So we are continuing with the first tutorial. We are continuing with quiz 1. We have read to you question 2b. We have shown you that the normal metal will behave like this. So this will be a general graph. So now let us proceed further. If you want to solve it for modulus of toughness, right, then you have to find area under this whole area. So now let me see, I have drawn these red lines. So until the end of the elastic region, you have this triangle, right? So until point B. So the area of this triangle will be your modulus of resilience. Then to this, you will add the area under this one. So what you can do is, from here, the yield point, you join the fracture point with a straight line, and you also make from here a parallel line, right? So now for this area under the curve, this portion will not be done because this is a this is a curve, so this we cannot do. We will have to neglect it. So maybe it will give you a few % of errors, but the rest of the area is divided into this rectangle, and this triangle, right? So this is how you will do. You have already found the area under this curve, which is the modulus of resilience. Now you will find the area of the rectangle and the area of the triangle and add all of them, and they will become your modulus of toughness. So your assumption, yield point and elastic limit are the same. There is no separate yielding region, right? Remember, on the previous page we showed you that sometimes in real materials it goes down a little after yield and then comes up a little, so there is a yielding region. So that if it is there, then we can't solve it easily. So the first is that you see the end of the elastic region and the beginning of the plastic region are the same point. Second, the plastic portion of the stress strain diagram is linear, not a curve. So there is a straight line from yield point to fracture stress. So these are the two assumptions. First assumption, that end of elastic region and beginning of plastic region are at the same point. So there is not a separate yield region. The second, that from B to D, from yield to fracture, it is not a curve but a straight line. Then you can solve it, right? So if you drew this diagram roughly, clearly, and if you wrote these assumptions, you should really be very happy that you really understand the question. If you did not, then you see, we discussed these issues and we solved these type of problems. And sometimes it means that if you made some errors, then now you will be able to see this error. So now let us start solving this part. I am showing you this diagram, right? And then I have done just rough that now I am removing the curved path. So I have a straight line region from here and I have another straight line region from here. So for the first part, the modulus of resilience is only this portion, So if this is a triangle, then half base into height. The height is the yield point and the base is the strain at yield point, right? So I am just here giving all the data that was given. The fracture strain was given, the modulus of elasticity was given, the yield point was given, the fracture stress was given. These things are given. Now for modulus of resilience, it is half epsilon y into sigma y, right? A strain at this point, so this is there. Because we know that in the elastic region, sigma is equal to E epsilon. So E is equal to sigma upon E, and right, then you can find what is the value of epsilon y, right? And then when you multiply this half epsilon y sigma y, then you just substitute the values and you get the answer as 0.521 megapascal, right? Megapascal, because a strain had no units, this had megapascals. But if you leave your answer here, all your calculations are right, but your final answer in terms of the unit is wrong. So you will get a small minus half or minus 1, because this is modulus of resilience, and the modulus is an energy unit. And we spent a few minutes in the class explaining to you that if you multiply this and divide this and so on, you will get joule per meter cube. So you can write megajoule. I am writing 0.521 into 10 raised to 6. So either you write into 10 raised to 6 joule per meter cube, or remove the 10 raised to 6 and write 0.521 mega, M capital M, joule per meter cube. So this will be the correct answer. Otherwise your calculations are right, but your unit is a stress unit, not an energy unit. So this was the first part, the modulus of resilience. Let us go to the next part, right? So as I explained to you earlier, that now we have divided this plastic region into two triangles. So modulus of toughness is this triangle, which was the modulus of resilience, which we already know, plus, right? First the rectangle. So the height of the rectangle is sigma y. Height of the rectangle is sigma y. This is given, and right, and the length, the total length here is until epsilon f, the fracture strain, minus the epsilon y, right? So these two values you have already calculated on the previous page. Epsilon f is given to you, and epsilon y you found it to be like this. So this is the area of the rectangle. This is the area of the rectangle. Then a triangle. So again, half base into height. Half base into height. So base is again this. So this is epsilon f minus epsilon y, which is given. And height. It is total length of this line, which is sigma f minus sigma y, right? So sigma f minus sigma y, and then you just do the calculations and so on. So the total answer is 48.7025 megajoule per meter cube. Megajoule per meter cube, or if the way I am writing, if you write into 10 raised to 6, then it is joule per meter cube, right? So it was not a very complex question. We had solved similar type of questions during the class, and those of you who paid attention during the class, and those of you who then revised the examples in the class and did the homework problems themselves would have done it. So again, alhamdulillah, I mean, you have seen that the maximum in the class, maximum score was like 18, 19 out of 20. The only thing was that the average is not where we would like to have it. Average should be a little higher. So but now you have done quiz 1 and quiz 2. Now you are preparing for the midterm. So even from now, if you really improve yourself and do the revisions in time, then it will not be a big issue, inshallah. Let us now move to quiz 2. And as before, there will be a small multiple choice and a small true false, right? But last time most of those multiple choice and true false were from chapter 1. This time most of them will be from chapter 6 on mechanical properties, right? So that is the same. Let us see how it goes. So let us go to the multiple choice part of quiz 2. A small grain size leads to more grain boundaries, higher strength, uniform properties. So you know that yes, if the grain size is small, it leads to all of the three things. There are more grain boundaries, the strength is higher, and the properties are more uniform. So all three is your answer. Next, length of grains will be maximum after cold rolling, recovery, recrystallization, grain growth. So again, if you understand your process, after cold rolling, the grains are very long. After recovery and recrystallization, they form into lumps and they start breaking into smaller ones. So the long, thin, needle-like ones will be right after cold rolling. So length of the grains will be maximum after cold rolling. Next, compared to annealing, after tempering, a strength of a metal is higher, lower, same, none of the above. You remember that when I was describing general heat treatment, then I said that for all metals and alloys, there is a stress relieving or annealing as one step. Then there is something called hardening and quenching. Then tempering. So after annealing, the metal is very soft. After hardening, the metal is very hard. So then after tempering, it is in between. It is harder than after annealing, but lower than after, right? So compared to annealing, right, here we are saying compared to annealing, after tempering, strength will be higher, right? Because annealing is the softest metal, and after tempering, it is higher than that, strength or hardness. Next, due to plastic deformation of a metal, changes occur in grain shape, dislocation arrangement, strength and hardness, or all three. What is your answer? Again, remember, if plastic deformation is there, grain shape will change, dislocation arrangement will change, strength and hardness will change. So your answer is all three. Next, change from ductile to brittle behavior with temperature happens for high strength alloys, FCC metals, low strength BCC metals, all three. So definitely not all three, right? But if you remember, we had just one graph where you were showing that when we take ductile to brittle transition temperature, then we told you that it is for one of these, right? So just go back there and have a quick look, that is it FCC metals or low strength BCC metals, and that is your answer. We now move to the true false part of the quiz, second quiz. The equation sigma is equal to sigma naught plus k upon root d is a type of Arrhenius equation, right? You know that it is the Hall-Page equation, but is it the Arrhenius type? The answer is false. Arrhenius type of equations, if you remember, is the power law type of equation. Power law type of equation. Some base is raised to a certain power. This is not Arrhenius type of equation. Second, heat treatment time and temperature do not affect the recrystallization process. What is your answer? Definitely false. You see, all heat treatment, all heat recrystallization is a type of, it is one step inside annealing and so on, and every heat treatment is affected by time and temperature. So not affected, no, it is false. Next, maximum change in strength and ductility occurs during the recrystallization stage. Remember, when we were doing the annealing curve, then, right, we have stress relief, right, and then recrystallization, and then grain growth. So maximum change in strength and ductility happens in which region? Yes, it happens during the recrystallization region. So this is true. After cold work such as rolling, material has many dislocations and other defects, and grains are stretched and deformed. What is your answer? Yes, it is true. You are doing cold rolling, so all the grains are being deformed and stretched, and of course whatever dislocations are there, you are doing serious level cold working and deformation, so they are also increasing. Next, heating for homogenization is also known as precipitation hardening. So there was just a one-page slide or 2 pages about general heat treatment. So is it written there that heating for homogenization is the same thing as precipitation hardening? No, this is false. So just go back. If you remember it, it is very nice. But otherwise, go back to those 1 or 2 page slides where you have done the general heat treatment process before doing the annealing in a detailed way.